My name's Caleb Ironman. I'm the territory manager for Lab Conco. Lab Conco is a privately held company based in Kansas City, Missouri, and Fort Scott, Kansas. And we manufacture fume hoods, VSCs, other lab enclosures, along with benchtop equipment like freeze dryers, central taps, nitrogen blowdown systems, glassware washers. I've been with the company for over 7 years. I just took over this Kansas City territory. I was out in Ohio, Michigan, Indiana, Kentucky, but spent a lot of times in the lab, degree, even worked in the lab as well. So I kind of know all the things that you probably shouldn't do that I did do, and then I learned from this job. But appreciate Kansas State EHS putting this on. I know this takes a lot of effort, a lot of time, but I think it's a great way to help push that safety culture, and it needs to be on the top of everybody's minds. But today we're going to talk about laminar flow enclosures. Being the territory rep, I get the phone call and they say, I need a hood. I'm like, great. What are you doing? Will a hood even fit in your laboratory? So just some common laboratory enclosures. You have a chemical fume hood, which is negatively pressurized and only offers personnel protection. There's no HEPA filter. So this is for chemical vapors, fumes, maybe inert particles. You also have a clean bench. This one particularly being a vertical clean bench, but as you can see with the construction here, we're going to take outside room air, draw it through the plenum where the motor's at, and push it through a HEPA filter where you have a positively pressurized ISO 5, typically with HEPA filter clean area. So it's like a mini clean room. We also have class 1 BSCs and HEPA filtered enclosures. Here it's going to be a negative pressure, similar to a fume hood, but those we're going to capture those particulates, possible biohazards, whatever that hazard may be. It's going to be drawn through the hood to protect the end user, and that air is going to pass through the HEPA filter and capture those particulates. That air is then returned to the room. If there is nuisance odors or a chemical hazard, they could potentially be exhausted to the outside via a canopy connection. And I think the primary one here, probably with Biosafety Week, here is going to be the Class 2 BSC. This provides protection to the end user, the sample, and the laboratory. You know, when everybody says, hey, I need a hood, let's identify what the hazard is. That's going to help dictate or direct us to the correct design to keep yourself and your colleagues safe, along potentially with your sample. It's just some common hazards that we see in the laboratory here. And I think the biggest question is then who or what are we trying to protect? Do we need personnel protection? Do we need sample protection? Do we need both? Uh, and then knowing those hazards will dictate how maybe if we need to exhaust to the outside. So primarily with it being Biosafety Week, we're dealing with biohazards, and really these enclosures, such as the clean bench, the class 2 biosafety cabinet, or a class 1 biosafety cabinet, was the key factor for it, or part is the HEPA filter. So a high efficiency particulate air. This was actually designed in the 1940s. Interestingly enough, it was kind of found in a German gas mask, and then the U.S. Army then worked on it more, and particularly in the Manhattan Project, and really developed for the radioactive particulates, where even a lot of the fume hoods, a lot of the enclosures that we speak of, they were really born through the Manhattan Project. But typically with the HEPA filter, you're going to have a filter media. You can see it's weaved in of many different sides. It's layered in continuous sheets. You're also going to have a filter frame, some sort of bonding agent, and a gasket. The other way we keep you or your sample safe is we have to have laminar air along with that HEPA filter. So it's uniform direction airflow, uniform velocity. And this helps prevent turbulence, whether that air is being drawn into the enclosure or being or your sample being bathed. And we need to keep that velocity and that laminarity true to help reduce turbulence, because if we get eddies or any type of turbulence going on, we could get cross-contamination or a loss of containment. So just to highlight again, to give you a little bit of the horizontal clean bench, room air is drawn in through the top. Typically there is a pre-filter, there's a plenum, the blower, and then it's pushed through this HEPA filter here and then passed along through the interior of the cabinet in a laminar form. This cabinet here or enclosure, you're only going to have personnel protection. And the question may be is, there's both horizontal and vertical clean benches. What type of samples are you going to be working with? If I'm going to have many test tubes opened up or plates, I could get cross-contamination potentially with horizontal. But the nice thing with the horizontal clean benches, you can place some larger equipment in there. There is no sash to it, so it helps for manipulations. I used to use one creating media or test media where I would have a pump, a filter system, and be filling up bottles in the lab of test media. The vertical clean bench may be better off if you're doing like PCR work or if you have multiple test tubes open. At least that air is being pushed down into your sample, so cross-contamination is less likely if you have multiple samples open at one time. The Class 1 biosafety cabinet, it's the complete opposite of a clean bench. We're actually going to have a negative draw of the air. You are going to have so-called the lab room air or dirty air crossing over your sample, but you're going to have personnel protection. And as that air passes over your sample, it will be pulled through the plenum, the blower itself, and then pass through a HEPA filter to capture those particulates or hazards. Again, you could canopy connect this type of enclosure to the outside. If there's nuisance odors, hazardous vapors, fumes, anything of that sort. Just want to point out, HEPA filters only capture particulates. They're not going to capture any off-gassing of chemicals or vapors of that sort. So the primary cabinet typically utilized in a BSL-2 or higher laboratory is a Class 2 biosafety cabinet. And it's essentially the marriage of the clean bench and a Class 1 BSC, where we're going to have both personnel and sample protection. Through this graph here, picture here, we're going to have negatively drawn air pulled into the front grill of the biosafety cabinet. It's going to go underneath the work surface. That air is dirty. We don't want that to be potentially contaminating our samples. It'll be drawn up through the BSC, through the plenum, and there's actually two sets of filters, an exhaust HEPA filter and a supply HEPA filter. That supply HEPA filter will have downflow air, typically about 55 feet per minute velocity. The inflow coming into the biosafety cabinet's about 105. That air will be recycled, typically on a 70-30 blend for an A2. But then the air is also exhausted back to the room, typically with a type A2 cabinet, but it will pass through a HEPA filter, so you'd still have the personnel and lab protection. So what is a Class 2 biosafety cabinet? Protective enclosure for safe handling of biohazard materials. Essentially what it's used for. Sometimes we see it utilized as kind of a mini clean room. We're seeing a lot more electronics being utilized in a biosafety cabinet instead of building out a full clean room. Or maybe that clean room is like an ISO 7 HEPA filtered air, where a BSC typically you're hitting about an ISO 5 to an ISO 4 type air. But again, it's going to protect the end user, the product, and the lab itself when recirculated back into the laboratory. Just some common applications I'm sure you're all familiar with. But we can maybe jump into the anatomy of the BSC. So you do have the internal work area. There should be some sort of armrest or grill. There's many different designs out there by different manufacturers. The work surface should be removable and even dished, preferably. So if there was a spill, it's contained, it's not running all over the place or underneath the work surface. But if that does occur, obviously a removable work surface should be there and of stainless steel construction. Typically 304 stainless steel is utilized. Everybody thinks stainless steel is bulletproof. It's not. Be careful of your cleaners and such. Bleach is rough on stainless steel. It'll pit it. If you have to utilize bleach, wipe it down with bleach, follow up with water. There are other oh germicides, sporicides, things that could be utilized. I would reach out to those vendors or even your local dealers here on campus who can help put you in touch. There's typically a protective glass shield. It can be raised to roughly about 22, 25 inches, depending on the manufacturer, but the BSC is typically ran operating sash height is of 8, 10, or 12 inches. Most commonly is 10-inch sash opening. It gives you some better ergonomics. The 8-inch is typically utilized quite often with the B2 cabinets, or if you do have to exhaust this BSC to the outside, it helps maybe reduce on the amount of air being exhausted. 12-inch I typically see in vivariums where you're trying to get maybe a small animal cage in and out of the BSC. Something that has changed that NSF has required, you may have a too high sash alarm, but I know on older BSCs, just about, not really that old, about 4 years ago, NSF required now a too low sash alarm. I know some end users were thinking, hey, if I lower the sash, maybe I have less cross contamination or a threat to myself, but now it will alarm where they want it within a 1/2 inch tolerance of where that preferred manufactured sash opening is at. You're also going to have a permanent airflow plenum, some sort of blower or blowers, depending on the model and manufacturer, the BSC, HEPA filters, and a supportive base stand. Your base stands, this one's just telescopic, but when you're going through the purchasing process, you may need to think, hey, does it need to be on casters? Do I need to pass it through doorways as well? A lot of times we see that in vivariums where these biosafety cabinets, they are very tall overall, and they just will not pass through a standard doorway unless you have a base stand that really drops all the way to the ground. So we talked about the HEPA filters here, but there will be two, supply and exhaust. But to point out just what the interior of a BSC looks like, here's the plenum that we have. That little orange cup there, that's a damper. We've changed our location here now, but there is always a damper for the certifier to help balance that BSC to make sure we get the proper inflow and downflow air. You're going to have the blower itself, and again, exhaust and supply HEPA filters. So a little bit better visualization or some animation. We can see the dirty room lab air get pulled in. That's going to protect the end user, goes under the work surface to the blower, to the plenum. About 70% of that air in a class 2 type A2 will be recirculated throughout the cabinet, and 30% of it will be exhausted through that exhaust HEPA filter, either back into the room or, if need be, exhausted to the outside. A little bit of visualization of that inflow. And I know we always talk about this in feet per minute, but maybe help relate it a little bit better. 100 feet per minute is roughly 1 mile per hour. Obviously, if we got a downflow air of 55 feet per minute, it's a 1/2 mile per hour. So all of these biosafety cabinets, whether it be a LabConco or another manufacturer, we have strict standards per NSF that we have to follow. But you need to have you need to have your end users educated about how to use a BSC. You can't be moving everything around quickly. You have to have that deliberate motion, slow and steady. because these airflows could be disrupted and you could potentially put yourself at risk, or your sample could get contaminated, or you're just doing work over and over again, wasting it, time, money, energy. You can see on the right-hand side with this downflow air, you can see how the smoke is pulled to the front and towards the back. And where that delineating point is, we call it the smoke split. And that'll come up here a little bit more through conversations. Again, NSF, we're required to provide additional testing. Every 5 years, we have to send our biosafety cabinets along with other manufacturers to have them tested. And a lot of times it's agar plates with a nebulizer. They'll typically use a spore. We want to see how well the biosafety cabinet protects the sample, and then we'll reverse that whole kind of setup to the outside to make sure nothing's escaping the BSC. But this is just a microbiology, just a challenge through NSF on a class 2 type A2. So I've ran into this issue many times in the field. A lot of people using maybe an open flame to inoculate a loop, things of that nature. That photo on the left side is the supply HEPA filter. I'll get the call of your BSC sucks. I've got all sorts of contamination problems. Take one look where I see the gas service fixture in the BSC. It's like, yeah, you burnt up the HEPA filter. So try and stay away from open flames, any high heat. Again, just not burning up the filter itself. 55 feet per minute downflow air. If you have too much heat in the biosafety cabinet, it's going to create turbulence and potentially a loss of containment as well. But it's going to affect that laminar downflow air. So recommendation, if you do have to inoculate or clean anything, maybe electric sterilizer is the best way to go. You could also go plastic, disposable loops, things of that nature, or disposable tools. Maybe not as green, but our key thing is keeping you safe and then your sample safe in a class 2 biosafety cabinet. And again, ANSI, NSF, and ANSI standard 49. You can take a look at, they'll define all the performance features of a biosafety cabinet that manufacturers have to meet. I know there are other biosafety cabinets out in the field that do not meet NSF 49 standards. Typically, you can see the NSF sticker listed right on the corner post of the BSC itself. But I know I'm starting to see a little bit more BSCs from overseas. I know there's even more requests for, hey, I need a small 2-foot biosafety cabinet, class 2 style. NSF requires that, hey, the working width of a BSC must be no less than 3 feet. So they want to make sure you have enough room to operate safely and aseptically. It will define the different types. For class 2 biosafety cabinets, you have types A1, A2, B1, B2, and C1, and we'll kind of review those here coming up. So again, just the image of the BSC, particularly the A2. And in this visualization, we have the work surface colored in blue. We're going to be recirculating the air to the back into the lab. So really, there should be no chemical usage inside the biosafety cabinet or even nuisance odors. The HEPA filter is not going to capture nuisance odors. So it's going to pass right back into the lab. So essentially that blue area, no chemicals should be utilized because there's zero exhaust to the outside. You can put a canopy connection on a class 2 type A2 biosafety cabinet though. And typically this is just for minute amounts of volatile chemicals, radionuclides, or samples with an unpleasant or nuisance odor. This canopy connection has to be made by the BSC manufacturer. You just can't put a snorkel over the top or retrofit your own from your local fab shop. There is going to be some air drawn through the canopy itself. This ducting here will then lead to a remote blower or your VAV system or exhaust system to exhaust that air to the outside. Again, a class 2 type A2, it's usually a 70-30% exhaust rate. So 70% of this air, once it hits your sample, will be brought back up to the plenum and recirculated again, where only 30% of that air is exhausted to the outside. With that canopy connection, all right, we kind of put that gradient to blue to purple. You've got to be careful with an A2. Like I said, it's minute amounts of chemicals. Everybody kind of asks me, well, what's minute? That's where you really have to go through the risk assessment, take a look at different guides or reach out to your EHS or safety officer. The issue with that 70-30 blend, somebody was wanting to use heat, and you can see the many service fixtures in there, so you know at least one of them was gas. Is granted, since we are exhausting an A2 cabinet to the outside, only 30% of that air within the cabinet is being exhausted to the outside, where that 70% is being recirculated. The gas valve might have been left on, or they had a high evaporation rate of a solvent, but that concentration or that atmosphere is going to keep building up within the biosafety cabinet where it does reach the lower explosive limit. And that's where an explosion can occur or a bigger fire. So typically what we utilize, it's a calculation that can be done. It comes from the Industrial Ventilation Manual of Recommended Practices. Industrial ventilation, I really feel like sets the rule book for everybody. Everybody takes information from them and always points back to them, whether it be from NSF, ANSI, NFPA, all these other different organizations. But you can figure out what that lower explosive limit is. And typically, you don't want it to exceed more than 25%. So the question again, though, is everybody comes to me, well, what do I need? Well, what is your hazard? How much is being utilized? How much is being evaporated? We need information from you about what's going on to at least provide a safe and economical enclosure. Just to recap on the A2, the nice thing is if you do have to exhaust to the outside, it can be manifolded or ganged with other BSCs or fume hoods, whether that be on a constant air volume system or VAV system, variable air volume system. They do have a lower exhaust rate, so operational costs are better. The cons are no dedicated exhaust airflow. That's where we kind of showed that purple region. We don't know how much is being exhausted or just that 30%. Can't handle all hazardous applications. And when it's always going to be a class 2 type A2 BSC. You can't convert it into a B or a C or a B1. So it is what it is. So, 40 years ago, God, it's probably coming up on 50 years ago now. I've been around too long. We had to find a solution for those hazardous vapors or chemical fumes being utilized in a BSC. So a type B was introduced by NSF. And this one particularly being a B1, where we're still protecting the end user and sample, but the air in the rear of the cabinet has a whole different plenum where it gets passed through a much larger exhaust filter and is exhausted to the outside. You can see here the remote blower. It's helping draw inflow air, and it's only providing supply air. These BSCs should be on a dedicated duct run because all that air that's going to be exhausted to the outside, it's all on your, all based off your remote blower on the roof line. The issue with that potentially is if that remote blower on the roof line does go down, NSF has a standard that within 15 seconds, the BSC should shut down. Well, I don't know what type of chemical work is being done or what biological hazards will happen, but in 15 seconds, that's still plenty of time where this blower, before it shuts down, it's going to positively pressurize the interior of the cabinet. And if I have no exhaust That cabinet will essentially what they call puffback all the biological hazards and chemical hazards will be just dumped right on you. So when working in this type of cabinet, typically your recirculating area is towards the front, your total exhaust is in the back. The tough thing is, as a HEPA filter loads, we saw that image of the smoke split or that video, it can move based off the filter loading. So either you have to run a smoke test to know where that line is at, that line of delineation, or the biggest thing is work in the rear of the cabinet. But nobody likes to work way back here, typically like this. Everybody gets a little lazy and brings it to the front. But it is an option when you do have you're generating chemical vapors. So to combat that, and really I don't see the B1s too often anymore. I don't know if you guys have any on campus or has anybody worked with a B1. I see more of the type 2s anymore. Now we have a total red area, total exhaust, no matter where that sample is at, 100% of that air, single pass air, is going to be exhausted straight to the outside. Again, it still has a single blower that only provides supply air. Same issue though, if a remote blower failure happens, this cabinet will become positively pressurized. It will shut down within 15 seconds once it detects the remote blower failure, but it can become positively pressurized and you have that chemical or biological puffback occur. The other thing, it's a great option if you do have those hazards, but these cabinets are a bear for the most part. The upfront cost, getting them installed, and then just the amount of air, this tempered air, we pay money to condition this air. It's single pass in and out. I mean, to put in even in perspective, I know like a 6 foot class 2 type B2, you're exhausting almost 1300 CFM on a 6 foot cabinet. A general 8 foot fume hood, again, this is just chemical, but an 8 foot fume hood, even larger with an 18-inch sash opening. B2s are only offered typically an 8-inch sash opening. At 80 feet per minute, you're exhausting like 800 feet per minute. I mean, they are just a energy hog. And typically we even call it B2 season where the phone rings. It's usually towards the end of summer, sometimes a little bit earlier when we see the cottonwood trees start spitting out cotton. The whole HVAC system just gets messed up. Everything's out of balance. Changing seasons, typically that early spring or late fall. The other issue with B2s should have a dedicated duct run. God, I just had one out in Colorado, big engineering firm in Kansas City. They're like, we're going to run B2s. We're going to gang them together on a VAV system. I said, don't do it, man. You're going to pay for it in the long run. The issue is, again, that's exhaust HEPA filter. It's about 6 inches of filter media, has a very high static pressure drop. 6 foot biosafety cabinet, it's 2.2 inches of static pressure drop. And that's really just the resistance or a measurement of how hard we have to pull that air through that media. And that's when the biosafety cabinet's brand new. As that HEPA filter loads, you're going to see additional static pressure drops increase, where typically you're going to want a remote blower that can accommodate upwards to about 4 to 5 inches of static pressure drop. The other issue is if you do gang them to one blower, it depends on the usage of the BSC. We can see here on this image, we have an inflow of 105 feet per minute, but maybe everybody prefers using that BSC on the left side because it's next to the window. I can look outside, watch, look at the birds. It begins to load up more, that HEPA filter compared to the other. Now you have a balancing act. Air is always going to take the path of least resistance. If you have a HEPA filter that's loaded up and one that's not quite as loaded, air is going to take the path of least resistance. Now both your BSCs don't have the proper inflow of 105 feet per minute. The one that has the filter loading is going to be reduced. The other one's going to increase. The issue is now all of a sudden you've got to play around with dampers and balance and everything else. It's just going to be constant maintenance all the time as that VSC gets utilized. So what do the officials or the guidance that is given on exhausting BSCs, particularly B2s? Let me see. NSF, ANSI, standard 49, they say should, not shall. I mean, NSF, they're always going to say you can try and do it. They want to allow for diversity, but CETA is an organization of a lot of the certifiers. They're just going to tell you straight up, just do dedicated duct run. It's going to save you the headaches. They don't want to come out on site to balance these BSCs, deal with your issues all the time. It's just it can be a real nightmare if you don't mechanically plan for this type of BSC. The other thing I see as well, when people call up and they say, hey, I need that BSC, I need a quote. I want it to be a B2. I feel like they're the safest. At times they're really not. You may spend more money than you need to, and just in terms of upfront cost, mechanical cost, and just the operational cost of it. But I mean, that's where a risk assessment needs to be done, and seek the guidance of your EHS officers or safety officer at your institution. Again, the pros: dedicated duct run, dedicated exhaust to the outside, excuse me. Cons: poor operational safety, must have dedicated exhaust run for each BSC, high operational costs, no flexibility. I have many people, they buy this B2 unit, they go, yeah, now I see what you were saying. Can I make it an A now, or can I recirculate back to the room? Sorry, you're stuck with that. So there is a class 2 type C1, and this kind of helps combat the issues that we see with the A's and the type A's and the type B biosafety cabinets. The total dedicated exhaust area is in the center of the cabinet from the front to the rear, about 66% of the work surface. On the outside wings, this air will recirculate. So all your hazardous chemical work can be done in this dished area here with 100% exhaust. That's going to help reduce the amount of CFM that you're going to be exhausting to the outside, which helps lower the operational cost. You have that clear line of delineation now versus a B1. You're not have to work all the way in the back of the cabinet. The nice thing with this BSC2 is you can switch it back to an A mode style where you can recirculate back into the laboratory, or as your research changes, you could switch to B, back and forth. You have flexibility. I'm not saying it's easy as flipping a switch, but at least you have diversity now with this style of BSC. I have some folks ask, well, what if in B mode, when we're exhausting 100%, if somebody places something on the wings? It's going to act like an A2 here, where 70% of that air is going to be reintroduced back into that exhaust area, or the chem zone, we call it, where it will be exhausted. So even if people make mistakes, there's some redundancy there to help keep those that atmosphere not as enriched, especially if utilizing a flammable solvent. Other nice thing as well, we talked about the issues of remote blower failure with this particular BSC. At B2s, they have to shut down within 15 seconds after detecting that remote blower failure. This BSC can help maintain negative pressure. There's actually 2 blowers in it where it can run upwards to 5 minutes. And that more or less gives everybody the opportunity to at least cap their samples, cap the solvent or whatever hazardous chemical they're utilizing, deglove, get the sash closed. So puffback will never occur with this particular BSC. So the construction is a little bit different where you have two blowers within this biosafety cabinet, one providing the supply air and drawing air through the front grill. But then you have a dedicated plenum where you can utilize in B mode, where this second blower here helps with the exhaust. And even when remote blower failure occurs. I mentioned before how B2s, they have a high static pressure drop due to the larger filter media. That filter media is roughly 6 inches. Static pressure drop starting at about 2.2 inches of water. That's a lot. I can't stress how much, if you guys don't know static pressure, that is quite a bit. A fume hood, typically it's like 0.25 inches of static pressure drop, maybe up to a half inch, depending on your duct run. I mean, a fume hood, it's even lower than that on a lot of them, about 0.15. So, 10%, but this BSC, it's always going to stay constant at that 0.25 inches of water because you have that other blower assisting. And that's also the same with the A2. But that helps with balancing as well. We mentioned the balancing of multiple BSCs getting together. You also need to balance on a B2, the remote blower up on the roof line. As that filter loads and you're not maintaining that proper inflow, you got to go up there and crank it up some more and some more. So you're just constantly balancing with B2s or the C1. Now that's not an issue anymore. Kind of set it and forget it. So just some comparisons of CFM, static pressure drops, the A2. The B1 is actually the lowest CFM, but it does have quite a static pressure range when trying to exhaust. The B2, exorbitant amount of air needed, high static pressure drop. And the C1 is pretty much similar to an A2. If safety isn't your concern or energy, it's maybe the operating costs. Everybody focuses on the dollars and cents. So that's just a rough breakdown. But in the 15-year span, just a standard A2 recirculate to the room, about $4,800, just cost of electricity and some and service. The canopy, we're exhausting air to the outside, so that becomes a additional operational cost. But just want to focus on that B2 because so many people think I want that BSC and I want to exhaust to the outside. It must be the safest thing out there. It's not always the safest if not utilized correctly, and it's not the most economical either. So, make some wise judgments. I'm sure everybody else could use 100 grand in their pocket for their lab for something else. And then just recap a little bit, the A2 intuitive workspace, easy to vent. A2 with canopy, yeah, minute amount of chemicals. What's minute? Depends on what chemical, what evaporation rates. Easy to vent, you can put it on VAV system, you can gang it. The B1, suitable with chemicals, but where do we have to work at within the BSC? Tough to say. That smoke split and that filter loading makes it difficult. B2, great for chemicals, single pass airflow, but a lot of mechanical upfront work, a lot of operational costs. I'm seeing the C1 come into everybody's plans a little bit more on larger projects, or many institutions are maybe utilizing a lot of A2s, but they always have like one C1 with a drop ready because you never know where that research is going to go or what new PI or researcher is going to come in. It allows flexibility. Obviously, just to recap again, A2, no exhaust unless with canopy. B2, 100%. The C1, you've got some flexibility. You can change it again in an A mode or B mode. So I've focus on the type of canopies when you're exhausting to the outside. I've had other safety officers go, scale, why do I maybe need a C1 compared to an A2? There's not, they won't be evaporating that much chemical. It's a minute amount. I think the key thing is when exhaust failure happens, how do these BSCs react? On the left, we have the A2 canopy. The flap on the right side, when in use, it opens up. And that helps with the balancing of the exhaust system. About 50 CFM runs through that uh, valve there on the right-hand side. And you can kind of see the wiring too. When that flap drops, there's a magnet on it, and then it'll instantly tell the biosafety cabinet to ramp up its blowers. We lost our remote blower exhaust or building exhaust system. NSF requires that, hey, you must ramp up those blowers, but we have an overpressure relief valve on the front. Well, we're dealing with minute amount of chemicals, typically with an A2 canopy connection. Yeah, they're minute, but how hazardous are they? Because when that remote blower building exhaust failure occurs, this overpressure relief valve right here, this flap opens up, and all those chemical vapors are going to be dumped right in front of the end user. The B2, which is a hard duct connection, again, that makes things more difficult with balancing. We may not have chemical exposure through the canopy, but we'll have it right in front of the end user where the sash is open with that puff back. The C1, it just has it doesn't have an overpressure relief valve. This is where I think it's key, where if you are dealing with some hazardous chemicals, I know maybe chloroform gets used, phenylchloroform gets used in DNA work. If we lose the building exhaust, there will be no dumping of any chemical fumes, vapors back into the laboratory. So I don't know. I still remember in Cincinnati, Ohio, where I was working at, I worked at Procter & Gamble quite a bit, and they had B2s. They were using the chloroform. Two pregnant ladies in the lab working in front of B2s. And we essentially got rid of that B2 due to the risk and the age. But then we were also able to put two C1s, so we were able to expand the workspace because it takes less air, and we were able to keep them safer, and they didn't have to change anything with their infrastructure. So that's the other thing, people maybe overlook is what happens when something does go into alarm. We can always talk about minute amounts, of chemical use. A lot of folks just, hey, canopy connection with an A2, not saying it's wrong, just consider the whole risk assessment or the whole process. What's the worst case scenario? So the other thing that we're running into more and more these days, we're seeing more and more automation in the biosafety cabinet. Biosafety cabinet was primarily designed to protect the end user. Now we're introducing automation. Concerns may be is, will the equipment fit in the biosafety cabinet? How much space is it going to take up in the biosafety cabinet? Through that animation, I showed that downflow air, that nice smoke split in the middle, and it was nice and laminar. Now, all of a sudden, we're jam-packing the BSC. There's less room in there. We're creating more turbulence, and we're accelerating the air. It's no different than like a rock in a river, creating an eddy. I mean, large equipment can fit in there. I would recommend doing smoke tests. We've worked hard with Sartorius. That's an amber 15 within there, but we've even got a custom for it, but we've got additional ports for all the surfaces that come in because it uses nitrogen compressed air. I thought some water, but then it has additional DNA ports or data ports, excuse me. But this at least helps keep things cleaner in the BSC, not just LabConco, but other biosafety cabinet manufacturers that can help out with these pass-throughs or make it a little bit cleaner, easier to use instead of having all this surfaces coming like through the front of the BSC. We don't want anything hanging out the front. You never know. Are you introducing something dirty? from the outside in and vice versa. So again, what are those hazards? Who and what do we need to protect? The more information you can give us, the better we can serve you to help find that economical and safe option. But not everything fits in the traditional biosafety cabinet. This automation is starting to get larger and larger. And some of these automation companies I have seen are kind of building their own so-called biosafety cabinet and not adhering to NSF 49 standards at all, or some of the challenges. It's like, oh, here's your clean little mini room here, BSC. You may want to take a look at, some of them may be doing it right, some may not, but I've had issues with the groups with CETA, primarily University of Michigan. They weren't pleased with some of these where there's no instructions at all of how to service it, when it needs to be serviced. Everybody's just kind of building it ad hoc as needed. But there are larger, what we call class 2 enclosures. We still apply, and other manufacturers, NSF standards, but NSF is yet to keep up with the demand, what we're seeing with automation. So it's not NSF regulated or certified, but there's a lot of manufacturers, including LabConco, who are making their best attempt to help the market to keep people and their samples safe with these larger style class 2 enclosures, I like to call them. I don't like to even call them a BSC. It's a class 2 enclosure. We're trying to take all the characteristics of a class 2 BSC, but we're going to call it an enclosure. As you can see, you have larger interior depth, height, so that helps reduce all that turbulence or that increased velocity, especially with that downflow air. Well, my equipment's really big. Well, great. We can link them together for you and create pass-through ports and things of that nature. There's even kill switches tied in where you can connect your equipment. Typically, there's some apparatus maybe moving up and down a rail system. It'll kill the automation if the sash is fully open. Nice thing too is with this larger equipment, a lot of times a service tech needs to come out, take a look at it, or perform work on it. Well, how do they do that in a traditional BSC? You've already got it jam-packed and everything they need to work on is on the back side of it. You can actually open up both sides of it. But only, once both sashes are down for operation though, and you do have a access area just to prep samples or whatever you need to do, or you could add portholes. Oh, I was kind of asked about lab layouts. This is just a traditional class or a BSL2 laboratory. There may or may not be a fume hood, but you can see the fume hood and biological safety cabinet. They're located towards the rear of the room. That's where the hazards are. Let's keep it away from the door swings, high traffic areas. If that's where the hazards truly are, why do I want many people walking by them when I'm coming right into the laboratory door? If you do have a new renovation coming up, there's many guides that you can take a look at. And then again, I can't stress enough, the K-State EHS group, they can be an asset for you too. And they're going to be the ones likely approving or disapproving of your layout or possibly have issues. So I would start those conversations early so you're not battling. But even with lab layouts and those guidelines I talked about, there's recommendations and based off what the clearances should be in front of fume hoods, biosafety cabinets. Since it's biosafety, we're going to focus on biosafety cabinets. NSF pretty much oversees everybody, biosafety manufacturers, kind of the gold standard in the US. But depending where your funding is coming from, NIH has a whole different set of rules and applications. So get familiar with those, or at least double check that or know how your funding's being utilized. I put down the LabConco minimums. I know sometimes we're dealt the hand that we're given, where yes, I've seen BSC side by side. Yes, I've seen them maybe a little bit narrower. We try to make as good of an enclosure or cabinet as possible. Sometimes you just have to do what you have to do, but And that's kind of part of the risk assessment, Hey, I really need two BSCs in here. Well, you don't have, 12 inches side by side or even 40 for NIH side by side. But worst case scenario is, okay, am I going to have more accidents, more exposure? Maybe put the BSCs side by side. But again, I would reach out to your EHS officers to check on that. Other thing too, I'm seeing with new labs and startups is something called BABA, or we term it BABA. It's Build America, Buy America. That was put in with the current administration to help promote manufacturing in the US. But that money, especially federal dollars, uh, could be a potential issue if you need something from overseas. So you want to take a look at that or make sure where your monies are coming from. All sorts of resources out there, but I can leave it open to questions. I think I'm just going over a bit here. So
if you separate, you have them too close together. If they're you only have them like 4 or 5 inches apart, can you put a separation wall in between them?
I have seen that. KBI actually did that. I've seen the separation wall. They did more for a high traffic area to reduce cross drafts. The key thing most time with our recommendation is at least 6 inches is for service. And the other issue is, I mean, in some of these photos I could have brought up or quizzed you guys what's wrong, what's right is slides. Hey, we got ducted BSC right up against the wall, right up next to the cabinet, duct it to the outside. I need to get in there to replace a board or something. It's located on the right hand side. I got this nice hinging door on the right side and the left. How the hell am I going to get to that? And it's ducted. I just can't pull it to the outside. So, that's where those space requirements are really needed. That's where even like considering floor to ceiling height. Um, that's a key aspect too, just for certification. I mean, I could also bring up, I know we talked all those canopy connections. Now I'm going different directions. I know the thought is everybody thinks a B2 is very safe. I'm exhausting the outside. Just give me the most bulletproof thing there is. There's no way I can scan that HEPA filter. Is there a tear in it? I don't know. You could do like a pitot tube type transverse, but even our engineers have drilled holes in the exhaust HEPA filter and use that same test method, and it passes. At least with these other canopy connections, you can see the filter media there, but fully scannable to detect all those leaks. But I think that's the key thing with any equipment in the lab. Yes, these BSL2 or tissue culture labs, they always seem to be a bowling alley of the lab. Not much space. You're trying to get the incubator in, the fridge, the minus 80 freezer, think about the layout. How is this going to be serviced? So, no, appreciate the question.
So I know biosafety, biosecurity, the big thing that we look at is positive and negative pressures in rooms.
Okay.
And when you're not operating the cabinet, that's not contributing to the overall air changes in the room. That can affect your pressure.
So A2 in recirculation mode, it shouldn't affect anything, but when you're exhausting to the outside, absolutely.
So how do you calculate the effect that's going to have if you're not certain how often you're going to use it, or is there a way to have your HVAC take a
So typically a room pressure controller could be utilized, BSC on, BSC off, or put a Venturi valve even above that. May help because the room pressure controller it'll notice the lab getting more negatively pressurized, so it's going to bring in more supply air. Uh, if you got the VAV system, you could use a Venturi controller. It's really just compared to a fume hood, it's not going to have a string potentiometer. It's just going to be on off per se. A lot of these biosafety cabinets too, maybe you don't want it completely off and it's exhausted to the outside, where you can have like a night setback setting where at least it's maybe not exhausting. Let's just say 400 CFM. It backs it off like 70% to help conserve on some energy. Number two, it keeps that space clean within the biosafety cabinet, so you don't have to purge all the time and clean. Even the advantage of that too is the biosafety cabinet also kind of becomes your own HEPA filter in the lab a little bit, keeps the lab clean. So, and you can even do that with a non-recirculating BSC too. Have a night setback where it can always be running constantly. An A2 recirculating, it'll bring that air back into the lab. But I'm seeing ANSI kind of made some changes for their latest edition of minimum air changes per hour. It was always kind of like that 6 to 12. Now it's like do whatever's safe. So I don't know if that's the best guidance. It's not bad though either. Each situation is unique. So it's just part of that whole risk assessment, what's really needed. I know the other thing too, I'm running into compounding pharmacies. They're required to have sometimes some very high air changes. I know everybody just takes the volume of the room, but if there's a lot of equipment in the room, that air volume may actually be smaller if you have a lot of casework or other equipment in there. I'm not saying you're like cheating the system, but you're truly getting the amount of air changes. You may be wanting 12, but if you have a room that's full, really full with equipment, it may really truly be half the volume and you're doubling the air changes per hour you really need. But if there's any other questions, I'll be here all day today and tomorrow, just out by the vendor booth. So again, thank you, K-State EHS, for having me, putting this whole event on. Happy to help out if you guys have any other questions. So appreciate everybody's time. Thank you.